Entropy, expected information from a process.
So probability comes down to axioms and variables. Given a finite sample space S equals T1 to TR, a set of numbers P1 to PR is a probability distribution on S if axiom 1, the P sum to 1. In sigma notation, I equals 1 to R, summed of the probability that X is T sub I, that sum has to be 1. The probabilities have to be non-negative, and that corresponds to a subset of a sample space. The probability of that subset is always non-negative. And if A and B are subsets of S that are disjoint, their intersection is the empty set, then the probability of A union B is the probability of A plus the probability of B. And notice we order the set from T1 to TR ordered by the index, the subscript. A variable X associated with S means that X is equal to T sub X for some index lowercase x. So probability also means good notation. So if X is associated with S, which is a subset of R, or perhaps subset of vector space, then uppercase X is the variable, lowercase x is the sample, or instance, or trial, or index. Axiom 1, the sum of the probabilities is 1. In sigma notation, using function notation, is the sum over x and s, p of x is equal to 1. Axiom 2, p is a function over s, has to be non-negative. And axiom 3 implies that if A is equal to the subset labeled T sub I1, T sub I2 up to T sub IK, then the probability of A is the probability of the individual outcomes summed together. But better notation is simply to say if A is a subset of S, then the probability of A is the sum over x and A, P of x. So let's review expected value and surprisal. We've got X is associated with sample space S, that's a subset of a vector space with probability distribution P of x. I may just say prob dist or even PD. So given a function f from S to R, the expected value of f of x with respect to the probability distribution P of x is E of f of x is the sum over x and s, f of T of x, P of x. A special case is just the expected value of the variable itself. Surprisal, or self-information of an event A with probability PR of A is, this is using our set notation, SI of A, the set A, is equal to negative log base 2 PR of A, the event or subset A. And this is in units of bits. But we like functions, so we let h of x be the surprisal by the event x is T sub x. And that defines a function h of x, which is the negative log base 2 p of x. Now, information entropy is the combination of these two. It is the expected value of the surprisal h of x on a sample space S with a given probability distribution p of x. It's the expected information from p of x over the entire sample space S.
So in particular, the expected value of self-information is called the Shannon entropy of the variable x, given by this formula. It's introduced by Claude Shannon in 1948 in a paper, A Mathematical Theory of Communication. For example, let's look at a spinner, this time with outcomes A, B, and C, and we'll just go ahead and use those labels. And the probability of A is a half, the probability of B and C is a fourth. The entropy, according to the formula, is given by this. Notice that the log base 2 of a half is negative 1, and the log base 2 of a fourth is negative 2. So we'll get a half times 1 plus a fourth times 2 plus a fourth times 2, and that's 3 halves bits. So in n trials that I guess the outcome for each trial, in half those trials I'll need one decision to learn the outcome, and in the other trials I'll need exactly 2 questions, as you can see by this binary tree. And the tree encodes binary strings. And notice that there's one string of length 1 and 2 of length 2. The average length is 3 halves. Let's look at another example again with a spinner. A, B, C, and D is the outcomes, but now with a half, a fourth, and C and D have probability of an eighth. This is the entropy given by the formula. It's a half times 1 plus a fourth times 2 plus an eighth times 3 plus an eighth times 3, and that's 9/4, which is 1.75 bits. Now let's use what's called Huffman encoding. We look at our probabilities for our outcomes. We form a decision with the two smallest probabilities, in this case C and D, and then replace the two smallest probabilities with their sum. And then we just repeat. We do it again, and we do it again. We get a binary tree that encodes outcomes with these binary strings. And the average code length is 1.75. So if we have n trials of x, denoted x1 to xn, the outcomes of the n trials can be encoded as binary strings. The shortest strings possible corresponds to the fewest binary decisions. The entropy in bits is the average over n of the mean length of a shortest string and the limit as n goes to infinity. That is, the entropy of n trials of x is approximately n times h of x for large n and approaches exact as n goes to infinity. So suppose we have outcomes that are equally likely. The probability is 1 over r for r outcomes. So the self-information is just the negative log base 2 of 1 over r, but that's just the log base 2 of r. Shannon entropy is defined as you see here. Alternatively, Shannon entropy is just the expected surprisal or self-information. That's the sum of I of x times p of x. If there are equally likely outcomes, then we end up with the sum of log base 2 of r times p of x. If the log base 2 of r doesn't involve any x's, the sum of the p of x's is 1, and therefore we get, if you have r equally likely outcomes, then the entropy is the log base 2 of r. Let's look at an example, a spinner with 3 equally likely outcomes, each with a probability of a third. The entropy is the log base 2 of 3, which is about 1.58496, so on and so forth. In one trial, we could form this kind of a tree, code length 1 and code length 2. That means we get 5/3 as the average for the 3. The average code length is 1.666 and repeating. But for 2 trials, we would have 9 possible outcomes. That would give us this kind of a tree. The average code length here is 1.6111, so on and so forth. In 3 trials, we would have 27 outcomes, and when we form, again, this is actually using Huffman encoding, we end up with an average code length of 1.6. 4 trials, 81 outcomes, an average code length of 1.5895, and you can see as the number of trials goes to infinity, we're approaching that log base 2 of 3. Again, we're using here Huffman encoding. Now, if we have a probability of 0, then the surprisal is infinity. Because the log base 2 of p of x, that would be negative infinity. So we instead need to use limits. The limit as p goes to 0 of p log base 2 of p is equal to 0. You can show that using calculus. So if p of x is equal to 0, when we set p of x log base 2 p of x equal to 0. Or we could say a better definition is Shannon entropy is a mean over non-zero probabilities.
So this is very important. Entropy depends only on non-zero probabilities. It's also important in applications. If an outcome is not in the data, then it has an empirical probability of 0. But that's not going to be a problem with our models because our models will depend only on non-zero probabilities.
So let's look at more than one variable. So joint surprisal means that it's the surprisal from x being t sub x and y being u sub y in the same trial. Again, it's the negative log of a probability, in this case the joint probability. And we can define I of x to be the surprisal from x equals t sub x and I of y to be the surprisal from y equals u sub y. And if x equals t of x, independent of y equals u sub y, then the joint probability is the product of the individual probabilities. And if we have independence, the self-information, surprisal, is equal to the sum of the surprisals. These are all functions on S, and even though I of x only has one variable, we can still think of it as a function of two variables. It just doesn't use the y. So that leads to the concept of joint entropy. So remember, this is our joint surprisal. Our joint entropy is the expected information from, or the expected joint surprisal, which is a double sum. It's the joint entropy of variables capital X and capital Y, the expected information from both X and Y. And notice that when we deal with pairs of outcomes, there are often pairs that have a probability of 0. So remember, we're actually only summing over non-zero probabilities. So let's look at an example of choosing cards. Jane chooses from 3 cards, numbers 0, 1, 2. John chooses a card from the 2 remaining. X is Jane's card, Y is John's card. This is the set of possible outcomes, each with a probability of a sixth of occurring. And we look at the joint entropy, but notice that 0, 0, 1, 1, and 2, 2 cannot happen because Jane and John can't have the same card. So therefore we have to be sure and sum over x not equal to y. Now the log base 2 of p of xy is the log base 2 of a sixth. And we can pull it out front, get negative log base 2 of a sixth times this double sum, but that double sum adds up to 1, and we just get log base 2 of 6.
So we have our entropy of a variable capital X, and I want to look at certainty. See, if p sub little x is 1 for some outcome, x is t sub x, then x is t sub x is certain to occur, and it's the only thing that can happen. All other probabilities have to be 0. There is no randomness. And that means we only look at the non-zero probabilities, and the only one we have is the p sub x equals 1, but the log base 2 of p sub x is the log base 2 of 1 is 0. So therefore, the entropy must be 0. Certainty corresponds to an entropy of 0. But by definition, the entropy is non-negative because the surprisal is non-negative. Thus, departure from certainty means we have to have an increase in entropy. In fact, the entropy of x is a measure of the uncertainty or the randomness in x taking on values from S. So let's look at a binary variable. Well, then binary entropy only has two probabilities, P0 and P1, and they sum to 1. So therefore, P0 is 1 minus P1, and if I let P replace P1, then my entropy of x is negative P log base 2 of P minus 1 minus P log base 2 of 1 minus P. As a function of P, h of P is just negative P log base 2 of P minus 1 minus P log base 2 of P, 1 minus P. If I take the derivative, I end up with negative log base 2 of P plus log base 2 of 1 minus P. The second derivative turns out to be negative, and I'll leave that for you to do as a homework. But the derivative is 0 if P is equal to half. Why? Well, 1 minus P is equal to a half, and negative log base 2 of a half plus log base 2 of a half is 0. In other words, the argmax of my entropy occurs when I get the uniform distribution P0 equals P1 equals a half. In general, maximum entropy, maximal uncertainty, corresponds to a uniform distribution. So entropy is a measure of uncertainty. Certainty, an outcome must occur. There's no randomness. But then as noise enters the system, outcomes become less certain. Uncertainty increases. And if not constrained, then uncertainty will increase until there is a uniform distribution. Maximal uncertainty, every outcome equally likely. Any outcome may occur and has the same chance of occurring as every other possible outcome of X. Much of our model building will be based on these ideas.
So entropy is expected information. Self-information or surprisal is the amount of information that can be learned from the occurrence of an event. Especially individual outcomes. I of x is negative log base 2 probability that x is x. Also, surprisal I of x is a function on the sample space. Entropy is the expected information from a variable x in that it's the expected value of that function I of x. And more generally, entropy is all the information expected from all the variables sampled by some process.